For this last chapter, we're not just leaving the Earth, but the entire solar system. In the early 1800s, astronomers understood our place within the Milky Way galaxy, but telescopes were just starting to get large enough to see beyond. However, the telescopes still weren't that great, so the nebular debate was about determining whether what they were seeing beyond the Milky Way were nearby clouds of dust or distant galaxies. To answer that question, the Mount Wilson Observatory was built near Los Angeles. It was about twice the size of any telescope built at that time, and in 1919 it had not yet been engulfed by the LA smog. The new telescope allowed Edwin Hubble to see that for the first time, that stuff outside the Milky Way were stars clustered in galaxies. The documentation of the number of galaxies is obviously an estimate here, but it does seem to be strongly supported that there are billions of galaxies with billions of stars. And this set the tone for a century of progress in the new branch of science called cosmology, which is devoted to the study of the structure and history of the entire universe. The galaxies found by Hubble and others can be classified into three types. Our Milky Way is a spiral galaxy, which has bright radiating arms where new stars are being formed. Elliptical galaxies lack those arms, and they are more densely populated with stars, so less stars are being formed in them already. Irregular galaxies have very few stars, making them more difficult to detect and making it harder to describe their shapes. However, these are probably the most common type, these irregular galaxies. Spiral galaxies are usually the youngest, and they create the other types of galaxies by either colliding together or at least coming close enough for gravity to have an impact on the shape. Just because Hubble found stars, and therefore galaxies, when he looked outside the Milky Way, it doesn't mean that nebulae don't also exist. These are areas within galaxies that can form stars or are the pieces left over from stars. Emission nebulae are clouds of hot gases and the most common type to form stars. Reflection nebulae are clouds of slightly larger particles than in the previous type, the emission nebulae. Reflection nebulae are seen from the reflection of light, often from nearby emission nebulae. Now, this type also commonly formed stars. Planetary nebulae were originally thought to be planets, but otherwise there is not much of a connection. These are clouds of dust thrown out by stars near the end of their lives. Your book lists dark nebulae separately from the bright nebulae, but really they have a lot more in common with emission and reflection nebulae than they do with planetary nebulae. The one difference here is that their particles are even larger than within emission and reflection nebulae, which makes them opaque, so light is typically reflected away from Earth instead of passing through, continuing toward Earth. Plus, these can produce stars, and they are more likely than the others to create planets. Hertzsprung-Russell diagrams are very commonly used in astronomy to show the distribution of types of stars, but they also relate the life history of stars, which change as they grow up. Most stars will spend the majority of their life in the curved band across the middle, known as the main sequence stars. However, they first start as nebulae, and after becoming a main sequence star, they can move across this chart both to the upper right and to the lower left. Now, if you have your book with the Hertzsprung-Russell diagram or just the HR diagram on it, it might be useful to follow along with this slide. How a star grows and dies depends on how much mass there is to start with. If there is just barely enough material to form a protostar, it will turn into a red dwarf, also called a cool red star within your textbook. And you'll find these on the bottom right of the HR diagram. Low temperatures burn off the fuel until it becomes a white dwarf. Nebulae with enough mass to form stars that fit on the main sequence burn hotter, throwing off gases as it expands to a red giant. Once additional gases are emitted, you're left with both a planetary nebula and a white dwarf, in spite of how this diagram suggests that the white dwarf is formed from the planetary nebula. Stars with huge amounts of mass form main sequence stars that occur on the upper left of the HR diagram. As they age, they increase in size by thousands of times. Heat and gas pressure try to expand it even more, while gravity is trying to counteract it. Eventually, these combinations of stresses cause a supernova explosion that will create incredibly massive objects, either a neutron star or a black hole. Edwin Hubble's observations on galaxies were not just that there's a whole bunch of them, but they are all also moving away from each other. The raisin bread analogy is often used to show that, but I think it's easier with a balloon. Because with a balloon, you can blow that balloon up by a couple inches, you can mark a bunch of dots on it, and you can measure the distance between the dots, blow the balloon up a little more, and repeat. And if you do that several times and graph the data, you'll see that between any 2 points, the distance is always increasing. Therefore, no matter where you are, all points move away from you. Now, it wasn't Hubble, but instead an astronomer and priest, who then proposed the Big Bang theory. If we reverse the expanding universe, we can determine how old the universe is. In other words, we can trace it back to where that balloon was deflated. Now, for many scientists, more convincing evidence was found by accident in 1964. Scientists working at Bell Laboratories in New Jersey tried to map the sky for radio signals to see if they could document sources of interference with radio transmissions. They found the same microwave background radiation falling on Earth no matter where in space they scanned. So basically, the universe has the same average temperature everywhere, suggesting a single beginning point for galaxies, but not for small things like solar systems or stars. So among cosmologists, there are still some questions about the Big Bang that are essentially unanswerable so far. Scientists can recreate the pressure and temperature conditions at a tiny fraction of a second after the Big Bang, but not at the moment of the bang. So what caused the bang to bang is unknown. Will the expansion that we see happen forever? As expansion continues, galaxies move farther apart, reducing the impact of gravity. So really, this question is whether or not there is enough matter to counteract the power of the explosion of the Big Bang. And the answer is probably not. And currently the universe seems to be expanding at an increasing rate, spreading out energy and matter. This will result in a situation known as the heat death of the universe, or what your book calls the Big Chill. However, if there is enough dark matter to cause the collapse of the universe, known as the Big Crunch, it is unknown if that focused energy will be the end of the universe, or it's enough to cause a new Big Bang.